what I want to do today is introduce other models, just to show you what you can do with Simulink and how easily you can do things in Simulink once you get your head around actually using it. Okay, so the first thing I want to look at is modeling a wind farm, alright? Or a wind turbine, or a wind farm. Obviously, wind farm is just a whole array of wind turbines. So this is your typical wind turbine curve. This is taken from an ESB presentation. So as you know who we are at this stage, I hope. So you have a cut-in speed, so you don't get any power from a wind turbine up to about 3.5 or 4 meters per second. Then you've got a sort of a cubed relationship. So in other words, as the speed goes up, the power is to the cube of the speed. So for this part of the curve, it's almost like a cubed relationship, right? But then it starts to even off. You get a plateau around 17, and you get cut off then at very high speeds. So if you want to model how much energy you're going to get from your wind turbines, you need to know this, what's called the power curve of your turbine. In terms of meters per second, a bit of a diversion. So 17 meters per second, is that high? What does that equate to in terms of the Beaufort scale? Anyone? So how do you measure wind speed? Or how do you guys interpret wind speed? What information do you need? What units do you want to know? Miles an hour. Well, actually, they usually say kilometers an hour now, really. Sorry, yeah?
Meters per second.
Okay, that accent gets me every time. Okay.
You're not the only one.
Meters per second, yeah. So you would even need meters per second. You're a rare species. And not because of your accent.
He is.
Huh?
He is.
Yeah.
Species.
Actually, I don't deal in meters per second, I don't deal in kilometers per hour. I would tend to deal in the Beaufort scale. You know, gale force, storm force. So this is a website I came across this morning in Croatian. Don't know why it came up in Croatian. But knots, if you're a sailor, have we any sailors here? Yeah, they complain at times when we don't talk in knots. But what's your name?
Ryan.
Ryan, do you deal in knots?
Not very often.
Right, okay.
In Typhoon.
Typhoon, good. Well, being into boating, you want to be able to Typhoon, yeah. Okay, so there's the Beaufort scale. Here's knots, here's kilometers per hour, here's meters per second. So you're all happy here, okay? So as you can see, 17 meters per second is about here. And in my lingo, it's between gale force, it's between 7 and 8 on the Beaufort scale. There's your yachter in terms of knots, and here's meters per second, and here's kilometers per hour, right? So last week, what was the highest speed recorded for the last couple of weeks in Ireland? What was the highest speed?
130 kilometers an hour.
I think it was 140 last week, off Cork and Kerry. So 140 is hurricane force, right? It's Beaufort scale 12. So it's greater than 32 meters per second. So you plateau here and you actually have to shut down. So wind turbines actually have to shut down at about 25 meters per second. Otherwise they might just blow up, essentially. The physical forces on them is too high. So this is from that site there. I just take these sites from random. I can't vouch for their scientific brilliance, but it looks okay to me, so I just used it. Again, cut-in speed, the third order characteristic, you plateau and then you cut out. Okay? This is your theoretical power. So how much power can you get from a wind turbine? Well, here's the velocity of the wind. So it's cubed. So this is a cubed relationship typically. So the kinetic energy in wind, how much energy is in wind? It depends on the cube of the wind. What else do you think it depends on? How much energy can you get from a wind turbine?
The blades.
The blade diameter. So there's the diameter of the blades. So if here's a wind turbine, funny one, there's the diameter of the blades. The density of air, okay? And essentially it's a half mv squared kinetic energy, right? But of course this is the theoretical power. What you actually get is quite a bit less than that. So the efficiency is typically 60% or less in terms of the maximum you can extract. So this is the actual power over the theoretical power is typically about 60%. Alright? So if you want to model a wind turbine, you can do all this fancy stuff, or you can just take the power curve from the manufacturer and model that instead. Because they've done all the work. They've put their turbine in a wind tunnel, small scale, and they've looked at the actual output, and then they can say, when we roll these things off the production line, we can guarantee you within plus or minus 2-3% that it will fit this curve. And you buy it on the basis of its curve. Okay? Because there's loads of factors that come into play, really. Okay. This is Airgrid's website. This was yesterday, the 18th of February 2014. So they have guys who model the output of wind farms, and as you can see for yesterday they did quite well. The forecast is in purple and the actual is in blue. And as you can see, things were quite good. I'll just see whether or not this will come up for today. It does, but of course Internet Explorer doesn't show us. Chrome is here, isn't it?
Yeah.
Okay, so this is today. So as you can see, we're now around here. So Airgrid, for some reason, put this information up. I suspect what they do is they like people like ourselves, academics, to take this data and see can we build better models, which is what I did with a master's student. Did I show you those results? Yeah. Okay, so you can see that they're doing okay as well today, but we're expecting, if you haven't been watching the weather forecasts, we're expecting bad weather this afternoon. So wind is increasing, so we're going to go from about 400 megawatts up to 1500 megawatts, or sorry, 1200 megawatts by this evening. Okay? So energy forecasting is obviously really, really important, which is what you guys are doing on your seats at the moment. This is why we're doing MATLAB, in case you didn't know. Okay, alright. So here is my model of a wind turbine. Much simpler than a house model in some ways. So what do we have? Needless to say, we have wind speed. So what I'm doing here is I'm reading in from the workspace data for wind speed as a function of time. The usual stuff. Okay, now I have a power curve. So I need to generate a power curve for the wind turbine, which will map wind speed to megawatts along the lines of these curves here. Okay? Alright, we need to make sure, number one, that the output of a wind turbine can be less than 0, and we need to make sure that it plateaus at whatever its output is. So we need to use another block, which is called a limiter block. So you pull this over from the library browser and stick it in line. So it says we want to essentially discipline what comes out of the polynomial block because it may produce some anomalies, as you'll see in a minute. So there's our power limiter. So this tells us what our actual modeled megawatts should be. We want to convert from megawatts. A megawatt is a megajoule per second, which is 1,000,000 joules per second. So we want to convert from megawatts to joules per second. Now, this model is actually running in minutes, right? I'm not sure if you can read that. I doubt if you can off the back. But the data I'm reading in, because I've taken it from live weather data from Galway, it's wind data in meters per second, but it's actually only recorded every minute. So the time unit for this model is minutes, right? So what we're saying is the wind speed is X, and then a minute later the wind speed is Y. But over that minute we need to model the output for that turbine. So we just take the previous value and multiply it by 60 seconds for that minute. So we don't look at variations within the minute. Therefore we multiply by 60. So we're converting from megawatts to megajoules per second. That's multiplied by 1,000,000, e to the power of 6. But then we need to convert again to per minute. So we multiply by 60 again. Alright? So I've said it a couple of times at this stage. Units, units, units. You need to know your units because your data won't make sense. Okay, so this gives us joules per second. So in other words, for a certain wind speed, meters per second, we get so many joules per second. Then of course we need to integrate it over the time of the model. One thing that I've introduced there is T-end. What does T-end mean, do you think? Is there a question? No. Okay. So T-end is a nice way of just saying, if you're reading in T from the wherever the base workspace, the model will only run until the end of the data. So it's a nice little shortcut. Not shortcut, but a nice little tie-in parameter to make sure the model only runs for the data you've got. Okay, so we integrate it to get joules, and then ultimately engineers don't talk in terms of joules of energy. Even we don't talk in terms of joules of energy. What's our domestic unit of energy?
Kilowatts. Kilowatt.
Joules.
Megawatt.
Oh God! You're killing me.
Kilowatt hour.
Hour, kilowatt hour. Okay, 20 cents per kilowatt hour. A kilowatt is not a unit of energy, it's a unit of power. Okay, get that right in your heads, right? Now, engineers don't talk in kilowatt hours unless they're baby engineers. When they grow up, they talk about megawatt hours or gigawatt hours. So, here we need to convert from joules to megawatt hour. And a megawatt hour is 3,600 by 10 to the power of 6 joules. So in other words, you divide the number of joules by 3,600 by 10 to the power of 6. So 1 megawatt hour is 3,600 mega joules. Alright? Yeah.
Why are you like scaling it up and then scaling it back down?
Because I like dealing in terms of... I want to bring it back to joules because fundamentally you guys know joules, but engineers fundamentally know megawatt hours. So you're right. Why am I wasting all that computation? It's just to, in any event, I want to reinforce the equivalence of units, right? But yes, you're right. There's no need to do that. But remember, you need to make sure your units are consistent. I don't care what you do, as long as your units are consistent, right? Okay, because remember, well, you know what I'm saying? Alright, a couple of things to say. So when you click on this polynomial block, so if you go to the library browser, there is a polynomial block that you drag over. And obviously we've seen the power limiter block. Or have we seen it yet? You haven't. Here's the power limiter block. So when you double click on this power limiter block, this is what you see. You specified an upper and a lower threshold. So again, the minimum is 0, the maximum is 10. So for our case it's 10 megawatts, right? What's the biggest wind turbine out there at the moment? Anyone? Hmm? No, the biggest one's about 6. Alright? So this one is 10. It's next generation wind turbine, okay? The problem with a 10 megawatt wind turbine is that they just get bigger and bigger and bigger, and nobody really wants them in their back gardens, as we know. Okay, so this is the limiter. This is the polynomial block. So this is the bit that reads in. So what's it doing? It's converting wind speeds into megawatts using the power curve. So what you need to do is you need to specify the coefficients of that curve. How do you do that? Well, we did it 2 weeks ago. So you do curve fitting, you get your polynomial coefficients, and you just stick them in there. Alright? So it calculates Pu given by the polynomial coefficient. P is sorted highest order to lowest order, just like polyval, or polyfit does, sorry. Polyval, yeah. So here is the script. So in other words, before this model can run, it needs to have data. It needs to have the polynomial coefficient, and it needs to have the wind speed. The wind speed is read in here. It can be read into the base workspace, or it could be read in by the script. Right? Doesn't matter. We showed that yesterday evening. You also need to specify the coefficients here. So that's done using this script. So this script here is essentially extracting the curve from that figure. Alright? Or this figure. So if this is 10 megawatts here, so we have a 10 megawatt turbine. So it generates 5 megawatts at about 10 meters per second, etc., right? So we want to extract that curve, so I do it using this script. So I take off the power points, pardon the expression. So we have 1, 2, 3, 4, as you can see, 0, 1, 2, 3, 4 meters per second, 0 power output. We start generating power around 5, 0.4, sorry. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, whatever. Yeah, I'm missing the points there, okay? 20 meters per second, right? Okay, I'm missing up my points and the commas there. So what I'm doing is I'm extracting the power curve here, I'm getting the size of it, and then I'm getting the speed data, which starts at 0 and goes up in terms of 1 up to the end of the size of the data. So in other words, what I'm doing here is I'm just extracting points on this curve. So 0, 1, 2, 3, 4, 5, 6, up to 20, and I'm taking the points off the curve at each point, right? And then I'm using polyval to extract the coefficients. Or polyfit. Sorry. Let me mix up those as well. So there's our coefficients. P coefficient 5. Fifth order, you just put in, remember, the speed and the power and the coefficient you want, which is 5. And it generates fifth order coefficient. Yeah.
What exactly is the apostrophe for?
Which one? This one?
Yeah.
Yeah. That's to turn it. We went through this before. It's to turn it on its side. You don't actually need to do that, but I like to do it in terms of I just like to have data in columns rather than rows. Plus, we saw you need it anyways for Simulink in terms of reading the time data. Okay, so what this will do is it will generate your coefficients, which is essentially what you put into this block here. So essentially what you're doing is we're reading in wind speed, we're converting it using this coefficients which we've derived from here. Alright? Everyone okay on that? Am I going too slow?
That coefficient was the 11.3%, you know that, don't you?
Huh?
That coefficient was the 11.3% of that.
That's why it's so low, is it?
I'm just saying, that was in that lab.
Yeah, but you have to generate your own sinusoidal model. Here it's just uses the polyfish, which is just the polynomial coefficients. Okay. Alright, I'm going to ask a question in a minute. Why am I not using third order here? Why am I using 5? We've already shown that the relationship between wind speed and power is a cubed relationship.
Because it's b squared as well.
No. Anyone?
Because it's a cutting cap.
Yeah. So if you were just to use a cubed relationship, so 0, 1, 2, 3, 4, 1, 8, 27, right? That's a cubed relationship. Now that relationship is true, but it's only true for this part of the curve. But because of this bit and this bit, we need to use a higher order curve to move to a more realistic version, which is actually like that. And then eventually it has to tail off as well. Okay? So that's why we use the 5th order rather than the 3rd order there. Okay, so this is our coefficients. Okay? So we're extracting the coefficients here. This script, this is actually from an exam paper 2012, right? So you extract the coefficients and, well, in this case I'm just showing you that if you actually plot the curve, it tells you how close the curve is to the actual data, which is this here. So this is the actual data in blue, and in green you see the 5th order equivalent. Okay, so is it a good fit? It's not bad. What's happening here?
And they're shooting on the ground.
Sorry?
And they're shooting. It's when they're shooting.
Yeah. It's going below 0. So essentially, you need to make sure that when you model your turbine, you are not generating negative energy. You're not sucking energy. Like, you understand what I'm saying here. A wind turbine doesn't produce negative energy. So that's why we use the power limiter to get rid of that. We've also got a bit of a problem here. But that's the nature of trying to model curves. You could go for a higher order curve, which would give you a better fit. Okay? Alright. So this is what this part, this is the one script, by the way. I'm just showing it over 2 different pages. And then you generate your time vector in terms of minutes. Minute 1, minute 2, minute 3, minute 4, minute 5. Okay? Because remember, ultimately you have to read in what the wind speed was for every minute that you want to model. And that's done by reading in the data from the spreadsheet. Okay? So when you read in this Excel spreadsheet, this is textual data, so it will just read this data. Okay, so it will read this data from the first, from 00 right down to the end of the month. Right? And so that's the actual wind speed data, and that's the actual minutes. Right? Okay. So just when you run this script, okay, you get all this data generated in the workspace. Here's time. Here's the full speed data. Here's our coefficients. So again, if you go to that script there, you'll see all the different parameters that are being read in. Whether it's M and N, being the size of the power curve, okay, speed data. So everything here is reflected in the workspace. Okay. So when you run that model, this is the overall model. What I've done is I've put in my signal viewer. So I want to look at the wind speed. I want to look at the output of the polynomial. I want to look at the output after the limiter. And then I want to look finally at the megawatts being generated. All right, the megawatt hours being generated by that wind turbine. And this is what you get. So here is the wind speed. All right. So as you can see, the wind speeds were quite low. It was a very cold month. I don't know if you remember. It was one of the cold winters we had. So wind speeds were quite low. In fact, in meters per second, they never exceeded 4. If you were to just use... Is that time right, by the way, folks? Yeah? Okay. So, we plug in the wind speeds, and this is what's coming out of the polynomial curve. Remember, the problem here with using the curve fitter, is that we're getting negative powers here. Okay? So for low wind speeds, we're actually dipping down here. And that's why when you run and we look at the signal after the polynomial, it's actually dipping below 0 in terms of megawatts. Alright? Now that's obviously unrealistic. So what I'm also showing you here is the output of the power limiter, which sets the minimum at 0. So we're getting rid of this error by putting in the power limiter. And that's that spike there, which is shown here as well. The units here are different. Alright? So you can see that literally for most of the month, the wind speeds were under 4 meters per second. Therefore, using our simple curve, we're actually generating negative megawatts. But the limiter takes out that error. And that's what you see here. It's only a tiny output we get at this point in the month, when the wind speeds peak. And we're just generating a tiny amount of energy, which means when we integrate it, it reaches a very small amount of megawatt hours. So in other words, that wind turbine generated no income for the month of December, because the wind speeds were so low.